All right, we'll get started. Today's lecture, I'll give you some more examples of doing inference, which is to say hypothesis testing and confidence interval, on some means. And in particular this time, rather than focusing on how the calculations get done in Excel, I'll focus on how the calculations would be done without using Excel, such as if these kinds of inference questions were being posed, just for example, on an exam paper. So this will be kind of useful revision of some of the concepts of inference that we've seen, hopefully tying some of the common pieces together as well, so that you'll see that there's just a couple of basic ingredients that go into every kind of inference problem that we have, and that will help you to kind of remember how to go about these things in each case. All right, so first of all, we have a data set that we're going to use to answer a question about, does it appear as though the wages that people earn are different depending on whether they live in the city or whether they live in the country? So we have a simple random sample of 500 people who are employed, they have jobs, and their wages were recorded, their annual wages in dollars. In addition to that, for each of these 500 people, it was recorded whether they lived in the city or in the country. So for each individual in this sample, we have two measurements: how much money they make and whether they live in the city or the country. And this urban variable, so urban meaning city, so people who live in urban areas are coded as being a 1. This is a 0, 1 variable. And people who live in the country are coded with a 0. All right, and I mean, I'm not really going to focus on Excel stuff today, but I'll just quickly show you what that data looks like in Excel. It just looks like that. So we have, wages and urban, and some of them are zeros as we go down. Obviously, we have more people in here that are coded as 1. So more people living in the city in this sample than living in the country. So we'll return to that question. And these are all the wages over here. You can grab that spreadsheet if you haven't already. So that's on the LMS. You can grab that and see what calculations have been done in order to produce what's in here. All right, so in total there are 417 people in this sample out of 500 who are living in the city and 83 living in the country. All right, like I said, we'll return to thinking about those numbers pretty soon. For the time being, though, let's concentrate on the question of the wages. So X1 is going to represent the wages of those in the urban areas, and X2 the wages of those in the country. There's the data there, so you can see. So we've kind of set up the data in two different ways. It's the same set of numbers. In the first case, we have all of these wages, and then corresponding to each of those is this 0, 1 variable that says, does this individual live in the city or the country? Over here, we've just kind of rearranged those observations so that all of the wages of the people who are living in the city are called X1. They're all collected in this column. And all of the wages of the people living in the country are collected over here. Okay? So, for instance, you can see that the first person in this sample who lives in the country has a wage of $72,600, and there it is up there. Okay? So just kind of split it into those two groups like that. All right, so two ways of representing the same wage data. In the first instance, we'll be interested in this one over here. All right, question. Is there evidence that mean wages differ between the city and the country on the basis of the information in this sample? All right, so what we have going on here, the first point about this is to recognise what kind of sampling situation that we're in. We're in an independent sample situation. We have a bunch of people living in the city and we have their wages. We have another bunch of people living in the country and we have their wages. Those two samples are independent of one another. They involve separate people sampled independently. And we know they were sampled independently because we were told right from the beginning we have a simple random sample, which means everybody is sampled independently from everybody else. Okay, so these two samples were drawn independently, and so we're dealing with independent samples. So a bunch of people in the city, a bunch of people in the country, separate people drawn independently. So that's the first thing to note before leaping into any form of statistics, is just to be sure you understand what the form of the sampling process is in the first place. All right, so we're obviously going to do a comparison of means here. So we want to compare average wages in the city to average wages in the country. So it's necessary to define notation for this. And if you have a question set up that's expressing something in words like this, then before doing any calculations, you'll want to make explicit what your notation is. So in this case, the notation, first of all, for the population means is going to be mu1 for those living in the city and mu2 for those living in the country. So you should specify this if it's not specified in a question, so that somebody reading it will know what you're talking about. When you start talking about mu1s and mu2s, we need to know. Now, if you set it up the other way around, so mu1 are the country wages and mu2 is the mean of the city wages, that's okay. You can put it either way around, just as long as you're consistent all the way through. There's not a right or wrong way to do that, just so long as you're clear and consistent with how you set these things up. All right, this is going to be a hypothesis test. So the question is asking us whether there's a difference between the means in the city and the country. So that's answered using a hypothesis test. And the hypotheses look like this. The null hypothesis is always an equality. So if the question is do they differ or not, then the null hypothesis is that they are equal. And then the alternative is that they are not equal, that they are different. So the form of the alternative hypothesis in this case is dictated by the words in the question, and in particular a single word, differ, here, is telling us that what we're looking for is a two-sided, two-tailed alternative down here. You can express it in either way. Mu1 equals mu2 is fine. Mu1 minus mu2 is also fine. I'll try showing this one as well. Okay, so it's just a skill to practice, I guess, is to how to just read the words in the question to set up the appropriate alternative hypothesis. So we're going to apply a 5% significance rule and to test this hypothesis using a critical value decision rule. What did I say? A 5% significance level and a critical value decision rule. All right. We have two types of decision rules, critical values and p-values. So we'll have a look at both of those today. But you should know how to deal with both of those. All right, here are the sample statistics then. And these are the sample statistics calculated from that data that I showed you in the spreadsheet. And again, looking ahead as if this were an exam situation, then obviously you would be given sample statistics like this. You would not be given 417 numbers and told to work out their samples, their sample mean and their sample standard deviation. That would be silly. So you would be given in some form or other some sample statistics like this that you could then work with to deal with a hypothesis test of this form. All of the information is there. We have the sample sizes in each case of these independent samples. We have the sample means. You can see that the sample mean for the city wages is different from the sample mean for the country wages. It's a bit higher. And the question that we're trying to answer with this kind of hypothesis test is the difference between this sample, is the difference between these sample means large enough to be considered significant? Okay. So is it possible that that difference is small enough that it could just be due to the normal sampling variation that we get because we're only taking a small sample out of the overall population? Or is that difference so large that even despite the sample that we have, we would deem it to be a significant difference and that we really do have different wages on average in the city from the country? So the hypothesis test is formalising that decision. We can see that the two sample means are different, but we want to know, are they significantly different at the 5% level? And we'll use the standard deviations here as well to help us out with that. All right. One of the things that we need in any of these, so we're going to do a t-test, right? And if we're doing a t-test for a hypothesis like this, we need a standard error. So the general form of a t-test is always kind of on the top line, we have a mean or a difference of means, and on the bottom line, we always have a standard error. So you need to be clear on how to work out the standard error of whatever is on the top line. So that's what we're going to do now. First of all, we'll work out the standard errors. We'll put together the pieces one by one here. We'll work out the standard errors of these individual means, and that's worth just revising, but it's also going to help us to get the standard error of the difference in means as well that we're headed towards. So the standard error of just the first sample mean all on its own is, by definition, the standard deviation divided by the square root of the sample size. So we just plug in those numbers that we've been given here, and that tells us what is the standard error of the x bar 1. And it's worth just dwelling on as a bit of a reminder, because we kind of have these terms that are sort of similar and it's easy to get confused about what we're talking about. When we talk about something like S or S1 or S2 and call that a standard deviation, then we're referring to standard deviation of data. Okay, so the actual numbers that have been recorded as the statistics for this particular variable, we calculate the sample standard deviation of those numbers. That's what the S is referring to, and we call that a standard deviation. As opposed to this standard error thing, which is in some sense a closely related concept because it is a standard deviation as well, but it's not a standard deviation of data, it's a standard deviation of the sampling distribution of an estimator such as a mean. Okay, so when we use the word standard error, we mean an estimated standard deviation, but for a mean or estimator rather than calculated directly from data. So two similar words, but they're referring to standard deviations of different things. So it's important to keep those two things separate in your minds as well, know which goes where. We particularly need to deal with these standard errors when we do t-tests and confidence intervals, which is what we're going to be doing for all of today. All right, exactly the same calculation can go on for the country statistics as well. The standard error of x bar 2 is found in exactly the same way. Okay, so we're now there. We have the standard errors for those sample means as well. All right, what we want to do is test the difference between the means. Okay, so our null hypothesis is that the two means are equal. So the basis of our test statistic is going to be the difference between the means, the difference between the sample means that we've calculated. Okay, so first of all, we'll calculate that. So x bar 1 minus x bar 2 is telling us that so far as our sample means are concerned, country wages are higher by $8,234.99. Okay, so that's the sample mean difference. The question is that big enough to be deemed to be a significant difference and that we really do have evidence of higher wages in the city or the country? Or is this within kind of the range of statistical sampling error? All right, we need the standard error of this difference in order to figure that out. So we're doing a difference of means test based on independent samples. So this is exactly the same test as we went through in, what was it, Tuesday's lecture. We did one of these. So we're just doing another one. And the standard error of the difference between the sample means in this independent samples case is given by this formula here. Okay, the standard error is given by the square root of the sum of the squares of the individual standard errors. And this is why we worked those out. Okay, we worked out those individual standard errors because we're going to need them in the independent samples case. So they can then just be substituted in, and we find that the standard error of the difference is 2,746. That number on its own doesn't mean a whole lot, but we need it to calculate the t-statistic. All right, so let's set about doing that then. The t-statistic has this form. So in general, a t-statistic always has this kind of ratio form. You know, the thing that you're interested in testing on the top line, the difference in the sample means. Now, I've put in the minus 0 here explicitly because we're interested in testing whether these two means are equal to one another. Or in other words, if their difference is equal to 0. Now, it might be possible. Occasionally what we want to do is to test not whether the difference is 0, but whether the difference is equal to something or other else. You know, if the difference is equal to 10 or something, right? Depending on whatever the question is, there might be some reason to want to know whether the difference between the means is given by some other specified number. And whatever that specified number there is, you would pop it in here into the t-statistic, okay? Most of the time in differences of means, it's a 0. All right, then we have a standard error on the bottom line. So this is the form of the t-statistic always has this kind of ratio form. Okay? It's often called a t-ratio. All right, we pop the numbers in, the difference of means on the top and the standard error of the difference of means on the bottom, and that works out to be 3.00 in this case. All right, so I'll file that away. That's all the calculation that we need to do in order to test this hypothesis. All that remains is to figure out what the decision rule is. We need something to decide. We need to know how to decide on the basis of that t-statistic whether we're going to reject the null hypothesis or not. So the form of the decision rule looks like this, and you should know the appropriate forms of the decision rules for the various kinds of hypotheses that we're dealing with. So the decision rule in this case is we're going to reject the null hypothesis if the absolute value of the t-statistic is greater than this critical value. Remember, when I initially set this up, I said we're going to use a critical value decision rule. So here, that's where this is coming in now. We're comparing the t-statistic to a critical value. The form of this decision rule is dictated by the form of the alternative hypothesis. So because this alternative hypothesis is not equals to, that means it's a two-tailed test, which means that the form of this decision rule here is a two-tailed decision rule. Okay, so we take the absolute value of the t-statistic, if necessary, it's positive in this case, but in general we take the absolute value of the t-statistic. And notice here in looking up the critical value, which we're about to do, we take the alpha divided by 2. So in a two-tailed test, what we're doing, if you kind of imagine the pictures that we have for this stuff, going back a couple of lectures, what we're doing is putting 0.025 of the probability in the top tail and 0.025 in the bottom tail of the distribution. Okay, so we're splitting that alpha into two parts, one in the top, one in the bottom, and hence the alpha on 2 enters our critical value here. And that's important because we need the right number here to look up in the critical value table. And then here's our degrees of freedom. So last lecture we mentioned that for a difference of means test in independent samples, the degrees of freedom is given by n1 plus n2 minus 2. So you add up the two individual sample sizes and then subtract 2. So that's the appropriate degrees of freedom for an independent samples test. Okay. You'll want to know that that's what it is. All right, that's the form of the two-tailed critical value decision rule for an independent samples test. Let's find out what that critical value actually is in this case. So alpha is 0.05. We were told to use a 5% level of significance, so there it is. And when that's halved, that's 0.025. And the degrees of freedom in this case is equal to 498. Okay, so we just add those together and subtract 2. All right, so our critical value decision rule can be written specifically like that. And that's telling us what to look up in the table now. So I've just taken an excerpt out of the table. I'll just draw your attention to as well this, this table briefly. This will be, I had meant to put this on the LMS already, I haven't quite yet, but this is the T table that you're going to get on your exam paper. It's basically the same one as what's in the textbooks. There's nothing new here, but just so that you're aware of exactly what it's going to look like, it will be at the end of the exam paper and you'll need to know how to find critical values out of this. So in this case, we're looking for T 0.025, okay, so that's where the alpha on 2 comes in. And then the degrees of freedom in this case is kind of huge, it's 498. So 498 is not in this table, but you just go and find, if the degrees of freedom that you want are not in the table, then you find the closest one. And so the closest one, we go all the way down the bottom, is going to be 200. And so the critical value we're looking for is that one, the 1.972. So, I mean, you've seen this kind of process before, but make sure that you're ready to do that kind of thing, that kind of critical value look up there. All right, so there's our critical value in that case, 1.972. And we're ready, okay? We have ourselves a fully functioning decision rule now. We have ourselves a t-statistic, and it's time to make a decision, which is, in this case, to reject the null hypothesis because the t-statistic is indeed greater than that critical value. So it's important to make all those details clear when you're going through one of these hypothesis tests. Okay, what's your statistic, or what are your hypotheses to start with? What's your notation? What's your hypotheses? What's your test statistic and how you got there? What's your decision rule? You should make that explicit. What's your decision on that basis? And then finally, just say, you know, a few words. A sentence is fine, to relate the finding of the hypothesis test back to the question, using words rather than statistical terminology. So you've decided to reject the null hypothesis, fine. What does that mean? It implies, in this case, that mean wages appear to be different at the 5% level when we compare the city to the country. So this difference of 8,000 and something that we found is large enough to be considered a statistically significant difference at the 5% level. So the evidence suggests that it's not just sampling noise, there really is a difference between these means, is what we would conclude from rejecting the null hypothesis. Now, as it happens, the sample mean for the city wages is bigger than the sample mean for the country wages. Now, notice we haven't tested whether it's bigger, we just tested whether it's different. So be careful with the choice of words in this final sentence here to say that the mean wages are different, because that's what we tested. Okay? If you wanted to test whether the mean wages in the country were higher than the mean wages in the, what did I say? Try again. The mean wages in the city were higher than mean wages in the country, then you would do a one-tail test. Okay? And then you could conclude that the mean wages had been found to be higher. So within the realms of the specific hypothesis test, just be careful to use the right words in your conclusion here to mimic the test that you've done and the words that set the question up in the first place, so that it's all kind of consistent all the way through. All right, so that's the test. That's just revising difference of means from last time. Hopefully that's helpful. We can also set up a confidence interval to measure the kind of the sampling uncertainty that surrounds the estimate of the difference between the wages for the people in the city and the country. So a confidence interval always has this kind of form. So just as t-statistics always have a form of, like, you know, an estimator minus the null value divided by a standard error, okay? The confidence interval always has the form of an estimator plus or minus the t-critical value, the two-tailed t-critical value, multiplied by the standard error. Okay, and that structure applies no matter what kind of statistic we're doing. Okay, whether it's just a simple mean, a proportion, a difference of means, a match pairs difference, doesn't matter. The confidence interval always has that kind of form of an estimator plus minus two-sided critical value times a standard error. All right, in this case, we've already figured out everything that's necessary to calculate that confidence interval. We've already got the mean difference, we've already got the two-sided or two-tailed critical value, and we've already got the standard error. So this is just a simple calculation at this point to find that the 95% confidence interval is that, 2,818 up to 13,651. So that's the confidence interval. Now, again, when you have a question such as this, almost certainly with probability approximately 1, there will be something after that to say interpret the confidence interval. So in other words, write a sentence to say, what does it mean, that thing that you just calculated, that interval? Say something about that in words. So what I've said here to start with is just to express the estimated difference between the means itself in words. And what's important about that is not only the words, the estimated difference is 8,234, but if it's relevant, then make use of the units of measurement. Okay, include that in your answer. That's important information. Okay, so the original data was measured in dollars. So once you take the mean of data that's measured in dollars, that mean is also in dollars. Okay, so you don't need to go around putting dollars on every single thing when you're doing your calculations. Okay, that's not necessary. But when you get to this final bit and you're just saying one or two sentences in words to sum up what it is that you've found, use the units of measurement. Okay, it helps to establish what's kind of the practical applicability of the statistical calculations that you've done. Okay. The interval in this case, so how you would describe this interval that you've calculated, is the interval between $2,818 up to $13,651. That contains the true, the population difference between the average wages with probability 0.95. That's the 95% confidence at the end there. All right, now, and just as a, so sometimes this will be useful to know as well, which is that the construction of the confidence interval that we went through, what was that, a week ago I think, was that the confidence interval contains all of the values that would not be rejected by a two-tailed hypothesis test. And that connection between the confidence interval and that two-tailed hypothesis test will sometimes be worth remarking on. Okay, let's return to this business about how many people in the city and how many people in the country we have in this particular sample. So the World Bank statistics, taken from the census actually, show that 89% of Australians live in urban areas. So areas deemed to be kind of the city from our perspective. Little blue star there, you can follow that and check out the statistics if you like. You'll see that Australia is a fairly urbanised country, in fact. So a lot of people live in the cities. Test whether the proportion of people who live in the city, the proportion of urban dwellers, differs significantly from this population proportion of 89%. Okay? Now, there's a reason we might want to do this, which we'll get to after we've done the test, but for the time being, let's just do the test. So now we're talking about testing a proportion. Okay? And the word proportion is explicitly in the question in this case. All right, so let's define our notation. So step number one, define the notation that we're interested in testing. So let's call the population proportion P, the proportion of people in Australia who live in urban areas. The hypotheses that we want to set up here, well, the null value is specified as being this population value of 89% from the census, from the World Bank statistics. Okay? So expressed as a proportion, that will be 0.89. Is the null value for P. And the question says, does it differ significantly? So again, the word differ is telling you that we're looking for a two-tail test. Okay, so the alternative that we've got here comes from this word, basically. All right, what evidence do we have in our sample? Well, we have 417 city dwellers in this sample out of a total of 500. So that tells us what the sample proportion is. Okay, there's enough information to work out that sample proportion. It's 417 out of 500, gives us 0.834. Okay, so the 0.834 is the proportion in the sample, and we're comparing that to 0.89 as the possible population value, because that's what we're interested in testing. We're going to do a t-test. If we're going to do a t-test, we need to find a standard error. When we're talking about proportions, then the standard error can be found, well, in two ways, but in this case where we don't have access to the well, we have the data in the spreadsheet, but for the purposes of this overhead, we're pretending as if we're kind of like sitting in an exam or something, and we don't have the spreadsheet. So in that case, the way to work out the standard error is like this. So this formula here is something that we worked out in tutorial maybe 6, I can't remember. We spent a bit of time doing some derivations with 0, 1 random variables and proportions and showing that there's two ways of getting at the standard deviation of those things. So we put some work into deriving this thing, and so and we did it for a reason. It's so that we can work out standard errors in this kind of situation. All right, so the standard error of the sample proportion is given by this number here, and you plug in the values and we get the 0.0167. So for a t-statistic, we've got everything we need. We've got an estimator here, the p-hat. We've got a population or a value under the null, which is this 0.89, and we have a standard error. Now, just before we leap any further, I'll just note that from the perspective of notation here, I started out setting everything up in terms of the p's and the p-hats. If you have a look at what we've done in our, well, tutorials in particular, and occasionally in the lecture notes and stuff like that, in these overheads and stuff like that as well, we've referred to those equally as being x bars and mu's, as if they're means. And the point is that they are means. Okay, so the data in the spreadsheet looks like this. Okay, and I'm now talking about this as being the data set here. So we can talk about proportions as p hats and p's, as the number of urban dwellers divided by the total number in the sample, which is exactly equivalent. It's identical to taking these 0 ones in this column right here and taking their sample mean. That will give you the proportion of urban dwellers as well. Okay, so that's the kind of stuff we were doing back in that tutorial. And you can see over here, that's exactly how I've done it. I've done it as an average. Okay. Okay. So what's the point of that? The point is when you're dealing with a proportion, from our perspective, it's equally valid to set up the notation in terms of a p hat and a p. That's fine. Okay, that works. Or you can call it a mean because it's also a mean. So a proportion is just an example of a mean. So if you only want to remember one set of notation, and from my perspective I quite like remembering only one set of notation rather than two, then you can set it up in terms of a mean, and that's fine. So the mean here is 0.89 under the null. The sample mean is the same as that proportion, which is the 0.834, and the standard error. So all the numbers are exactly the same. We've just called them different things now. Let's do the calculation then. We have the x bar, and we have the standard error, and we have the null value, so we have everything we need to calculate a t-statistic. Okay, so the t-statistic is the difference between the estimator, the x bar, the null value, which is m, 0.89, and the standard error on the bottom line gives us a t-statistic of minus 3.362. All right, so I'll file that away. Now, didn't say, oh no, it did say, p-value decision rule, there we go. So we're going to practice one of those in the same way that you would be looking to practice one of these if it were, let's say, an exam. So the way that we have calculated p-values during the semester is to use Excel, to use the t-distribution command. You know, there are those 3 versions of the t-distribution command that tell you to do a t-distribution two-tail or right-tail or t-distribution, depending on what kind of decision rule that you're implementing. Now, Excel's not available to you in an exam. Okay, it's available to you all the rest of the time. So it's important that you learn how to use it for practical purposes. But for the exam, the way that it will work is some p-values will have been already calculated for you, and you'll be given a menu of choices, and you get to choose which is the appropriate p-value corresponding to the t-statistic that you've calculated. So I'm illustrating that here by providing myself with a menu of 3 p-values. That's a very small menu. You might be given a bigger menu than that just to make the choice a little bit more interesting. But let's have a look at how this is working. The TDF thing here is a t-distributed random variable. Now, the form of the p-value, the way that it's defined in terms of probabilities, is different depending on the type of test you're doing, depending on the form of the alternative hypothesis. Okay, so if the alternative hypothesis is two-tailed, which is what we're dealing with here, this is a two-tailed test right here. So for a two-tailed test, the p-value is this thing. It's twice the probability that this t-distributed random variable exceeds the absolute value of the t-statistic. Okay, so basically this calculation here is saying, now you won't have to do this calculation, you'll just have to recognise the form of the probability, but this calculation is saying that you'll grab this t-statistic, take its absolute value, find the probability of being greater than the absolute value of that t-statistic, and then because it's a two-tailed test, you multiply that probability by 2. Okay, and that's the appropriate p-value if you're doing a two-tailed test. Okay. We went through that in lots of detail a few lectures ago now. And if you work that out, you get 0.008 in this case. If it were a lower tail test, then the probability is simply, the p-value is simply the probability that the t-distribution is less than t. So for a lower tail test, it's a less than probability. For an upper tail test, it's a greater than probability. Okay. So in this instance, I've just worked out those p-values, those 3 p-values, corresponding to one possible value of the t-statistic. Okay. You could be given p-values corresponding to other values of t as well. Oh, yeah. All right, so we have a two-tailed test here because of the form of the alternative hypothesis, and the p-value for this test that we want to decide on is therefore the 0.0008. All right, so that's how a p-value approach would be implemented in an exam situation. The decision rule, therefore, is to reject the null hypothesis if that p-value is less than alpha, which in this case is, again, 5% or 0.05. So the decision rule for a p-value test is always nice and easy. Is p less than alpha? That's it. That's always your decision rule. No matter how easy or complicated your p-value calculation is, the decision rule is always that simple. And in this case it is. So the p-value is less than alpha, so we do reject the null hypothesis. All right, so that's the implementation of that. So that's just kind of revising a basic test of a mean, really, in the case where the mean is a proportion in this situation. So that's revision of what we did a little while ago now. The words that you would use to sum up something like this, we would be interested in this kind of situation in doing this kind of test because this kind of test is looking at whether the sample that we have drawn is apparently representative of the city-country balance of place of residence in Australia. Okay, so 89% city dwellers is the population proportion, according to the census. In this particular sample, we got 83.4%, and this hypothesis test is telling us that that's different, statistically significantly different from the population value of 0.89. So we may have some concern about whether the sample that we have drawn is actually accurately representing the balance of city versus country dwellers. We seem to have a few more country people in there, apparently, because the proportion of the city dwellers is a bit less. So we might do that kind of test there as a test of representativeness, perhaps. All right, here's another example. An innovative weight loss program was trialled on 19 participants. This is the same program that you'll have a look at in next week's tutorial as well. So there's a few, yeah, I've got, well, a number of measurements about that arising out of this particular study that I did the stats for. It's kind of interesting. In this case, we'll just look at how the program went for weight loss. So there are a bunch of people who joined the study who were overweight, and their body mass index, so their weight divided by the square of their height, was calculated before they entered the program, and then I think it was a 12-week program, it was recorded after as well to see what change in the BMI they had recorded. So sample statistics provided, I'll show you those in a second. The question is there evidence that those on the program lose weight? All right, so the data looks something like this, and the first point to get your head around here is what kind of sample are we dealing with? Okay, what's the situation, what's the comparison that we're wanting to make? Well, now we're dealing with a matched pairs situation. So it's matched pairs because we have two sets of measurements before and after. Okay, so for each individual, each of the 19 individuals in this program, we've got one measurement on the BMI before they started and another measurement on the BMI after they finished. So those two measurements are matched because they both belong to the same individual in the study. Okay, so that's how you think about, you know, does this comparison that we're looking for appear to be matched pairs, or does it appear to be an independent sample? This is not an independent sample because this number here and this number here both belong to the same person. Okay, so they're matched, they're a pair. All right, so these are the BMIs of the individual people. So the first individual was 33.48 before the study started and ended up at 30.36 and so on down the list. Those are some pretty big BMIs. They're bigger than you'd like to be. All right, notation then. So we will denote X1I and X2I as being those observations that I just showed you, the before and after BMIs. Again, if you want to refer to them the other way around, that's fine. Just be clear and consistent all the way through as to which one is X1 and which one is X2, and that's fine. And then because we're doing matched pairs, then we set up these differences, these Ds. Okay, this is something we do with matched pairs data when we're looking for differences. We do not do this with independent samples. So that this, setting up this DI thing only makes sense in matched pairs. And what we're doing with these DIs is just simply taking the differences here. Okay, so 30.36 minus 33.48, 29.56 minus 35. The individual weight losses are being calculated in these DIs. All right, notation for the means then. So we're going to do a comparison of means here in this matched pairs situation. Mu1 can be the population mean of the BMIs for those eligible to enter the program in the first place. I don't remember precisely what the eligibility criteria were to enter this study, but you had to be in not great shape anyhow. So we have these kind of, we're talking about a population of people who satisfy these criteria who need to lose some weight, and we have an average weight for those in the population. And then of those people, we have an average weight of those who actually carry out the program. So what would be the mean, the population mean of weight loss, the population mean of BMI of those who complete the program. And then we're interested in particular in the difference between these. So the mu D is the population mean of the weight loss, and we want to know, the original question is, do people lose weight on average? So is the mu D negative? So that tells us the hypothesis, right? Once we've set up that notation, it tells us what the hypothesis should be. And notice in this case, we have a less than test. Well, notice in this case, for a start, the mu D under the null hypothesis is 0. So the null hypothesis is always equals. Okay, so the null hypothesis says on average, the program is useless, people don't lose weight. Okay? And then the alternative hypothesis is lower tail, because it asks specifically, is there evidence that the participants lose weight? It's not saying, do they change weight while they're on the program? It's saying, do they lose weight? So it's specifically looking for a movement downwards in the weight, so that translates into a lower tail alternative. All right, so here are our sample statistics then. So the X1s are the before BMIs, so the average BMI for those entering the program was 37.477, with a standard deviation there. The average BMI at the end of the program of those 19 individuals was 34.577. Okay. All right, so that's less. All right, so the average, the sample mean BMI was less than it was at the start. Is that a significant difference, is the question. Okay, so people have, in some sense, lost weight, but is that a significant loss from the perspective of we only got 19 people here? I mean, is this just statistical noise, or is there really something going on? Here are the statistics for the Ds, and this is what we focus on, right? So the average weight loss across those 19 people was to shift the BMI down by 2.92 points. And we've got standard deviations for each of those as well. And again, these are the kinds of things that if this was being set up in an exam kind of situation, then obviously those kind of statistics would be provided. Okay, you don't need to calculate those from lots and lots of observations. You might need to calculate a mean or a standard deviation from a small number of observations, but not 19. That's wasting time. All right, if we're doing a matched pairs test then, we don't need those numbers. So I've given them to you, but we don't actually need them here. The only thing that's relevant in a matched pairs test is, are the statistics for the Ds, for the differences. Okay, so if we're doing a matched pairs test, we just need the D bar and the standard deviation. So the rest of the stuff might be there, but it's just a distraction. We don't need it to do the test. All right, so let's do the test then. The D bar is minus 2.9. The standard deviation of that is 1.5. We want to do a t-test. To do a t-test, we need a standard error. So the standard error calculation is basically the same standard error calculation we saw earlier in the lecture as well. We take the standard deviation divided by the square root of n. Okay? So the standard deviation is 0.357 in this case. Now the t-statistic. Again, the t-statistic has the usual kind of standard form. Sample mean, in this case d bar, minus the value under the null hypothesis, which is 0. Okay, I haven't colour-coded this time, but hopefully you can see where all the pieces are coming from. The standard error that we just worked out, the 0.357, and so our t-statistic is minus 8.188. Now, the decision rule. So we'll do a critical value decision rule again, just for one more bit of practice at using the critical value table. We have a one-sided alternative hypothesis here, so the form of the critical value decision rule is different this time. Because it's in the lower tail, because the alternative hypothesis has a less than, our decision rule has to have a less than. And the critical value has to have a minus sign out the front. We're looking down the left-hand tail, in the negative tail of the t-distribution, so we need a minus sign there as well. So that's the form of the decision rule dictated by a less than alternative like this. To look up the critical value itself, we'll just pop into the table. Well, yeah, we'll just pop into the table. We'll use alpha equals 0.05. N minus 1 is 18 here because n is 19. So 0.05. So it's not alpha on 2 here, notice. So it's important to get that straight as well. If it's a one-tailed test, we just use the alpha here. If it's a two-tailed test, we use the alpha divided by 2. All right, so it's a one-tailed test, so the 0.05 and the degrees of freedom are 18, n minus 1. So here is our critical value. That's our t critical value, the 1.734, with a minus sign out the front because we're looking in the lower tail of the t-distribution. So we're sorted. We have a decision rule. The t-statistic is minus 8. The critical value is minus 1.7, so the t-statistic is less than the critical value. We reject the null hypothesis in this case. And the words here are pretty simple. We can conclude at the 5% level of significance that the individuals are losing weight and that is statistically significant at the 5% level. So even though we only have 19 participants, the size of the weight loss was sufficiently large for us to conclude that it was this is genuine weight loss and not just kind of statistical noise in a small sample. There you go. You should know all that stuff. It will be very useful to you to know all that stuff, if I can't hint any more obviously than that.